I've spent some part of my life figuring out how to make machines automate stuff. And it's pretty obvious that we can automate many of the things that we humans have been proud of doing for a long time. And the question is then sort of what's the future of the human condition in that kind of situation? So more particularly, I see technology is about taking sort of human goals and making them be able to be automatically executed by machines. And the human goals that we've had in the past have been like, move this object from here to there and use a forklift truck to do it rather than our own hands. Now, the things that we can do automatically are more intellectual kinds of things. They're things that have traditionally been the profession's work, so to speak. These are things that we are going to be able to do by machine. And the question then is, so sort of the flow is, the machine is able to execute things, but something or someone has to define what should its goals be, what is it trying to execute. And people sort of talk about, well, what's the future of the intelligent machines, and are the intelligent machines going to take over and decide what to do for themselves and things like this. I think the thing one has to realize is that while sort of figuring out, given a goal, how to execute it is something that can meaningfully be automated, the actual inventing of the goal is not something that in some sense has a path to automation. That is, when we say how do we figure out goals for ourselves? How do we, how are goals defined? They tend to be defined for a given human by their own personal history, their cultural environment, the history of our civilization, things like that. Goals are something that is sort of a uniquely human kind of thing. It's something that almost doesn't make any sense. We ask, what's the goal of our machine? Well, we might have given it a goal when we built the machine. Actually, the thing that makes this more kind of poignant for me is I spent a lot of time studying basic science about computation, and I realized something from that. That's a little bit of a longer story, but basically the question would be, if we think about sort of intelligence and things that might have goals, things that might have purposes, what kinds of things can have intelligence or purpose or something of that kind? Right now, we know one great example of things with intelligence and purpose, and that's us and our brains and our own human intelligence and so on. The question is, what else is like that? And the answer, which I had sort of at first assumed, was that, well, there are these systems in nature and they do what they do, but sort of human intelligence is far beyond anything that sort of just exists naturally in the world. It's something that's the result of all of this elaborate process of evolution and all this kind of thing. It's a thing that we can that really stands apart from the rest of what exists in the universe. What I realized as a result of a whole bunch of science that I did was that isn't the case. That even when we look at, well, a funny version of this, my children always give me a hard time for this particular quote, is, one says, the weather has a mind of its own. Well, that's a sort of an animistic type statement, and it seems like it has no place in kind of modern scientific thinking. But actually, that statement is not as silly as it at first seems, because what that's representing is, if we think about a brain, what is a brain doing? A brain is taking certain input, it's computing things, it's causing certain actions to happen, it's effectively generating certain output. We can think about all sorts of systems as effectively doing computations, whether it's a brain, whether it's a cloud responding to sort of the different thermal environment that it finds itself in, these kinds of things. And then we can ask ourselves, are our brains doing vastly more sophisticated computation than happens in these fluids in the atmosphere or whatever else? And I had at first assumed that the answer to that was yes. We're carefully evolved, we're doing much more sophisticated stuff than any of the systems in nature. But actually it turns out that's not the case. It turns out that there's this sort of very broad equivalence between the kinds of computations that different kinds of systems do. And so that realization sort of makes the question of the human condition a little bit more poignant, because we might say, well, look, there's one thing we've got. We're special. We've got all this intelligence and all these things which nothing else can have. But that's not true. there are all these different systems in nature that are pretty much equivalent in terms of their sort of computational or, for that matter, intellectual kinds of capabilities. But then the question that, what makes us different from all these things? Well, what makes us different is the particulars of our history and which gives us our kind of notions of purpose and goals and so on. So this is sort of a long way of saying when we have the box on the desk that, thinks as well as any brain does, the thing it doesn't have intrinsically is the kind of the goals and purposes that we have, because those are really defined by our particulars, our particular biology, our particular psychology, our particular kind of cultural history and so on. So, I think that the thing we have to think about as we sort of think about sort of the future of these things is there's goals. That's what the humans contribute. That's what our civilization contributes. There's execution of those goals. That's what we can increasingly automate. We've been automating it for thousands of years. We will succeed in having very good automation of those goals. And I've spent some significant part of my life building technology to essentially go from a human concept of a goal to something that actually gets done in the world. There are many questions that come from this. So an example of one that I'm thinking about a lot right now is, okay, we've got these great AIs and they're able to execute goals. The question is, how do we tell them what to do? So one answer to that is, well, just talk to them, right? And so, like you talk to Wolfram Alpha or Siri or whatever, we are understanding the natural language there, human utterances, and we're doing something based on those utterances. And it works pretty well when you're sort of when you're holding up your phone and you're asking one question. It's a pretty successful way to communicate, to use natural language. When you want to say something longer and more complicated, it doesn't work very well. I just had this experience. I've been interested in sort of teaching programming to the world and to kids and so on. So I was just writing this book and I was writing exercises, something that it's a very bizarre thing for me to do because I've never done exercises myself, I think, in any textbook. But anyway, I was writing exercises, and these exercises are typically of the form, write a piece of code to do X. Okay? And at the beginning of the book, when the exercises are really simple, it's pretty easy to write the English to say, write a piece of code to, make a list of numbers from 1 to 10 or something. But by the end of the book, it was getting bizarrely frustrating because I was thinking, this is the exercise I want to write. I know what the code is supposed to be. Now, how on earth am I going to write the piece of English text that represents that code? And what I increasingly realized is some of this text was starting to sound like, the language that you would find in a patent or something like this, some very ornate, precise, kind of stylized English. And so the realization from that is, the thing I've spent a large part of my life doing, which is building computer languages, is actually not such a bad idea, because in a computer language, you do get to represent, kinds of more sophisticated concepts in a clean way, which can be progressively built up in a way that isn't possible in natural language. So one of the things that I'm interested in there is kind of this question of, okay, so how do we communicate goals to AIs? How do we talk to the AIs, so to speak? And that's and my basic conclusion is that it's sort of a mixture. Human natural language is good up to a point, and human natural language has evolved to describe what we actually typically encounter in the world, things that exist from nature, things that we have chosen to build in the world. These are things which human natural language has sort of evolved to describe. But there's a lot that actually exists out there in the world for which human natural language doesn't have descriptions yet. Even though our AI systems might effectively find those descriptions, we don't have ways to say those ourselves. But also we have when it comes to describing more sophisticated things, the kinds of things that people actually sort of build big programs to do, we don't have a good way to describe those things in human natural language, but we can build languages that do describe that. So one of the things I've been many different things I'm interested in. So an example of a question that I've been curious about recently, but I'm going to get back to the main thread in a second. But one question I've been interested in is, what does the world look like when most people can write code? So we had a transition maybe 500 years ago or something when, from a time when only the scribes, so to speak, and a small set of the population were literate and could write, natural language. Today, a small fraction of the population can write code. Most of the code they can write is really for computers only. It's not code where any human is expected. You don't understand things by reading code. But there will come a time when as a result of things I've tried to do, particularly where the code is high enough level that it is a sort of minimal description of what you're trying to do, and it's something where, for example, when you have a contract, you write contracts. They're written in English. You try and make the English as precise as possible. There will be a time when most contracts are written in code, where there's a precise representation that, it might be for in cases where it's a computer says, can I use this API to do this? Well, there's some service level agreement that's going on there that isn't a human contract. It's something that's written in a piece of code that is understandable to humans, but also executable by the machines, so that you don't, this question of whether, can I do this according to this contract? It's an automatic question. And that's something where, that's one tiny example of how the world starts to change when sort of most people can write and read code. And I think the interesting sort of language point is today we have computer languages which for the most part are intended for computers only. They're not really intended for humans to read and understand. They're intended to tell computers in detail what to do. Then we have natural language, which is intended for human-to-human communication. And I've been trying to build this knowledge-based language where it's intended for communication between humans and machines in a way where humans can read it and machines can understand it too, and where we're kind of incorporating a lot of this sort of existing knowledge of the world into the language in the same way that in human natural language we are constantly sort of incorporating knowledge of the world into the language because it helps us in communicating things. But so, one branch that I'm really interested in right now is this question of what does the world look like when most people can read and write code. Another, coming back to the sort of main question of kind of, okay, so what's the future of the humans in a world where once we can describe what we want to do, things can get done kind of automatically, so to speak. What do the humans do? And I've been kind of interested in one of my little hobby projects is trying to understand the evolution of kind of human purposes over time. So today, we've got all kinds of purposes. We sit and have a big discussion about purposes, which presumably has some purpose. We do all the different things that we do in the world. If you look back, 1,000 years, people's purposes were really different. I mean, it's like, how do I, get my food? How do I prevent, how do I keep myself, safe? All these kinds of things, which in the, modern Western world, for the most part, those purposes have kind of, you don't spend a large fraction of your life thinking about those purposes. So you've sort of evolved to different kinds of purposes. And from the point of view of 1,000 years ago, some of the purposes people have today, some of the things people do today will seem utterly bizarre, like one that I think of, I walk on a treadmill every day, right? Now, imagine that from 1,000 years ago saying, well, somebody's going to spend, an hour walking on a treadmill, and what a crazy thing to do. Why would one ever do that? Well, I think then as we look sort of to one of the things that amuses me in today's world is the fraction of people who play video games that take them back to the Middle Ages, so to speak. So we're kind of, we think about, so the question is, what happens in the future? What do people do in the future? Particularly, what do people do in a time when a lot of purposes that we have today are generated by scarcity of one kind or another. We have, there are scarce resources in the world, people want to get more of something, and so on. There is scarce time in our lives, and so on. Eventually, those forms of scarcity will disappear. I think the most dramatic discontinuity will surely be when we achieve, effective human immortality, which, whether it's achieved by biology or digitally, is not a clear, interesting question. But that is something which I think is pretty inevitably will be achieved. And an awful lot of current human purposes have to do with, well, I'm only going to live a certain time, so I better get a bunch of things done. So the question that I'm curious about is, what does it look like at a time when sort of things can be executed automatically? If you have a purpose, it can be executed automatically. You don't have the kinds of drivers for purpose that we have today. What does it look like? And do people end up? There are some bizarre hypotheses one might have. One hypothesis is, well, people will look back to a time when there was scarcity, and when people could say, well, what did people choose to do at that time? Just as for a very long part of history, and even to some extent today, people look back to antiquity, to the religions created long in the past, and so on, and say, well, when those things were created, then people were really had the important issues going on. Let's look at how they resolved them at that time. And one of my more bizarre hypotheses is today is sort of the first time in history at which a large fraction of what goes on in the world is being recorded in some way or another. And so there will be in the future, this is the first time at which that's been broadly happening. And so one of the things that could happen in the future when sort of the current set of purposes aren't really issues anymore, people would say, well, at a time when people really did have scarcities of various kinds, what did they choose to do? Let's go study that time as carefully as possible. And then every detail of what we do in our time, which ends up getting recorded, ends up becoming sort of fodder for, well, that's what it really means to be a human with purposes. Let's go do what they did in 2015 or whatever. I think that's a slightly, I think that's a slightly extreme version, although, when we look at the large span of history and going back to the kinds of places people have looked at purposes from a few thousand years ago, it's not quite as crazy as it might at first seem. But I think one of the issues is, one of the things I would like to have a great answer to is, okay, so what do the derivatives of humans of the future, what do they end up choosing to do with themselves? It's one of the potential bad outcomes is, well, they're just playing video games all the time. That the future of civilization is everybody's playing video games. They're playing World of Warcraft of the future, so to speak. The history of AI. It's kind of it's a funny history, and it's sort of an evolving word in its use in technical language, so to speak. In these years, AI is very popular, and people have some idea of what it means. And so we can talk about AI, and people have some notion of what we're talking about. I watched this evolution over the course of probably, must be basically 40 years now. And it's gone from being, well, in the 60s, before I was aware of what was going on, everybody thought, let me even go further back. Back when computers were first being developed in the 1940s and 1950s, the typical title of a book about computers or an article about computers in a newspaper was Giant Electronic Brains. The idea was that just as things like bulldozers have automated, and steam engines and so on, automated mechanical work, so computers will automate intellectual work. There'll be a giant electronic brain. That promise turned out to be harder than what people expected. People didn't know what was involved in making brain-like activity, and it turned out it wasn't very easy. Now there are even there are amusing movies from the 1950s. Computers as AIs got into sort of science fiction-ish portrayals from long ago. There's one cute one called Desk Set, which is about basically an IBM computer being installed in some company and making everybody not have a job to do and so on. It's kind of cute because the computer gets asked a bunch of reference library questions in this movie. And so as we were building Wolfram Alpha, one of the questions was, can we do all of the reference library questions from the Desk Set movie from 1953 or whenever it was? And eventually we could do them all, finally, in 2009. The thing that happened was, so there was first a great deal of optimism that we could automate intellectual work in the same way as we've been able to automate mechanical work. And a lot of government money got spent on that in the early 1960s and so on, and it basically just didn't work. And things happened, like there was this particular approach to well, neural networks had been discussed, particularly by McCulloch and Pitts in 1943, and they'd kind of come up with this model for how brains conceptually, formally might work. And they made the observation that their sort of brain-like model would correspond to being able to do kinds of computations like Turing machines. And they had the idea of, they knew about the universal Turing machine idea from Alan Turing from 1936. And so from that it kind of emerged, well, we can make these brain-like neural networks that will be able to be general computers. And in fact, that thinking was the way that Turing's work on universal computation flowed into the practical work that was done by the ENIAC folk and von Neumann and people like that on practical computers. It didn't come directly from Turing machines. It came through this sort of side road of neural networks. But then they set up simple neural networks, and the simple neural networks didn't do terribly interesting things. There's a guy called Frank Rosenblatt who invented these things called perceptrons, which were kind of one-layer neural networks. Then the sort of terrible thing that happened in the 60s to neural networks was Marvin Minsky and Seymour Papert wrote this book called Perceptrons, where they basically proved that perceptrons couldn't do anything interesting, which is correct. Their proof is absolutely correct. They can only make sort of linear distinctions between things. The problem was that people, and this is a typical sort of academic trait or something, that people said, well, these guys have written a proof that these neural networks can't do anything interesting, therefore no neural networks can do anything interesting, so let's forget about neural networks. And so that happened for a while. Meanwhile, there was sort of there were these couple of different approaches to AI, one based on sort of really understanding at a formal level, sort of symbolically, how does the world work, and the other based on kind of doing statistics and kind of probabilistic kinds of things. There was sort of well, are we going to be able to do symbolic AI? And one of the sort of test cases of that is, can we teach a computer to do something like integrals? Can we teach a computer to do calculus? That was sort of a test case from the late 1960s for AI. Then there were things like machine translation that people thought would be, a good example of what computers could do and things like this. Anyway, the basic bottom line was by I guess the early 70s, that stuff had kind of crashed. Then there was a phase where there were these things called expert systems, which were the next round of AI, which came up in the late 70s, early 80s, which were sort of teach a machine from a human, have a machine learn the rules that an expert uses to figure out what to do, and so on. That kind of petered out. In fact, my first company ended up somewhat against my wishes going into somewhat into that direction in the end. But in any case, that was the next phase, and then kind of AI kind of became this crazy sort of nobody really does that. It's a fake thing. It doesn't, there's nothing interesting there for quite a long time. There's been this question of AI. I myself have been interested in sort of how do you make an AI-like thing since I was a kid, basically, which is a depressingly long time ago now. I was interested in particular in how do you sort of take the knowledge that us humans accumulate, or have accumulated in our civilization, how do you automate kind of answering questions on the basis of this knowledge and so on. And I thought about this first actually around 1980, and I sort of thought about how do you do that sort of symbolically by actually building a systematic sort of system that can break down questions and turn them into symbolic things and answer them. And I kind of concluded, well, to really do this well, we have to have sort of a brain-like thing that involves sort of fuzzy questions, fuzzy answers, these kinds of things. And I thought, building a brain is kind of hard. I worked on it a bit. I worked on neural networks even at that time. Couldn't really make much interesting progress, kind of put it aside for a while. I kind of have this approach of having these, difficult projects, which I try to think about every some number of years and try and figure out, is the ambient technology in the world ready to actually do this project now? So I, back in, now in the mid, 2002, 3-ish time frame, I was like, okay, I should think about this, make a sort of computational knowledge system. I should think about that question again. What does it take to do it? And I realized that actually the science that I had done pretty much showed that my original belief about how one had to do this was completely wrong. I mean, my original belief had been, in order to make a serious sort of computational knowledge system, you first have to build a brain-like thing, then you have to feed it knowledge, just like we learn things in sort of standard education, and then you'll have sort of a good computational knowledge system. But what I realized as a result of a bunch of science that I'd done was that sort of there wasn't, this was, as I was talking about earlier, I mean, there isn't sort of this bright line between what is intelligent and what is merely computational. You know, I had kind of assumed that there was some magic thing, sort of the transistor of intelligence or something, that was this sort of magic mechanism that allows us to be, you know, vastly more capable than anything that is merely computational. And it turned out, you know, what I kind of showed scientifically is that that's just not the case. So, you know, one of the challenges always in somebody like me at least is, how do you take these kind of basic science, sort of almost philosophical conclusions and actually decide to do something on the basis of them? Do you actually, you know, take that philosophical dog food and believe in it? And for me, taking that was, okay, so actually build technology. If it's possible to do this, actually build a technology stack that actually does it. And so that's what led to Wolfram Alpha, for example. And what I discovered from that is that, yes, it really works to be able to take a large collection of sort of the knowledge that's in the world and automatically answer questions on the basis of it using what are essentially merely computational techniques. Now, there's a footnote to that, which is kind of an important footnote, which is that when one thinks of what is merely computational, one often thinks, okay, one's writing a program. How does one write a program? Well, a programmer sits down and they say, I want to write a program that does this. You know, I'll write this module, I'll write that module. I think about, you know, how am I going to achieve what I'm trying to achieve with this program? Every sort of step has, you know, I'm taking one step at a time to get to where I want to go. Okay? What I had discovered was that there was sort of an alternative way to do engineering, which is something much more analogous to what biology does in evolution and so on, which is just to say, you know, out there in this sort of computational universe of possible programs, there's an infinite number of possible programs. If you just go out and look in that space of possible programs, even just look at random at 1 trillion programs and say, what do these programs do? One might have thought that programs which are simple enough that one can actually have good coverage of sort of all possible programs of a given kind, one might think that none of them would do anything interesting. They'd all be just simple programs that do simple things. You know, who cares? But actually what I had found scientifically was that that wasn't the case, and that even very simple programs, particularly I looked at cellular automata, but also Turing machines, lots of other kinds of things, even very simple examples of those kinds of programs can already do very sophisticated things. And you know, one of my conclusions was that's really interesting in terms of understanding how nature works, but that's also important in terms of finding technology. In effect, what we normally do when we build a program is we sort of build step by step this piece of technology. The other thing we can do is just go out into the computational universe and mine technology out of the computational universe. And you know, typically the challenge is the same challenge that we face in doing physical mining. That is, we find this amazing supply of, I don't know, let's say iron with magnetic properties, or cobalt or something, or gadolinium with some special, you know, magnetic properties. Say, okay, great, it has these wonderful magnetic properties. What do we do with this? Well, the question is, can we connect that capability to an actual human purpose, to something a goal that we have, to something we want that technology to be able to do? In the case of magnetic materials, we have plenty of ways to do that. What we find is that there are all sorts of wonderful things in nature. The question is, can we entrain them into our technology by finding some useful human purpose that they achieve? And in terms of programs, sort of the same story. There are all kinds of programs out there, even very tiny programs that do very complicated things. The question is, can we entrain them for some useful human purpose? And this is a thing that we learned how to do, of, you know, given a particular purpose, given a particular goal, just go exhaustively search 1 trillion programs and find one that does a useful thing for that purpose. And sometimes those programs are doing things like making random number generators, hash coding systems, doing things that have to do with natural language understanding. Sometimes they're doing more creative things. Like one thing we did a bunch of years ago now was having a music generation system where you just basically press a button, will go search a big space of programs. It'll find a program that, according to some heuristic, matches some particular musical style, then it'll play you that. And this is sort of an interesting case, actually, because it's a case of kind of automated creativity. People say, well, you've got these machines, they'll never be, if there's one thing that humans are better at, it's being creative. Actually, the thing that I find most interesting with that little music creation site is that I had kind of assumed that people would say, oh, I need some inspiration, composers and so on would say, I need some inspiration about my composition, and then maybe I can dress up that inspiration using a computer. But instead, I run into people who say, that's kind of a nice site that you have. I go there to get inspiration for some kind of little core of a tune, which I then dress up as a human to make it be meaningful and fit into what I'm trying to do. So it's kind of a case where we're seeing that this attribute of sort of originality, creativity, is something that is readily available in this computational universe. It's sort of the same thing as saying, go out into the physical world and go find these beautiful places to photograph, so to speak, in the world. They exist already. It's a question of us picking the one we care about to look at. But I mean, backing up to this question of so what sort of the arc of AI. So one of the things that we discovered was that it really does, as a practical engineering matter, there's really a lot that you can do by basically discovering programs in the computational universe of possibilities rather than merely building a program step by step. What we also spend a lot of time doing is building this thing called language, which is this knowledge-based language, which tries to sort of incorporate the knowledge of the world right into the language. So kind of the traditional approach of computer languages is to say, let's make a little computer language that represents the operations that computers intrinsically know how to do. Allocating memory, setting values of variables, iterating over things, changing program counters, whatever else. It's sort of a slightly higher level version of that, but it's fundamentally one's telling computers to do things in their own terms. And that's been kind of the tradition of basic programming languages for 50 years. My theory about these things is, let's try and make a language which panders not to the computers, but to the humans, and try to make a language where the language is as much as possible just being able to take kind of what the humans think of and convert it into some form that the computers can understand. And part of what the humans think of is the humans know about the world. They know about, the existence of Cambridge, Massachusetts, or they know something about, that there'll be a sunrise tomorrow type thing. And the question is, can you encapsulate the knowledge that we've accumulated both in science and in kind of the collection of data in the world into a language which we can use to communicate with computers? And that's sort of the big achievement of my last 30 years or something, has been to be able to do that. One of the things that is significant there is when you're trying to solve this sort of problem of doing computational knowledge, having such a language, that's the way you need to encode sort of things about the world and things you can do in the world. But in terms of the sort of the arc of AI, so one sort of set of things that would be considered sort of very AI-ish is being able to take the knowledge of the world and be able to answer questions on the basis of the knowledge that one has of the world. Being able to, and so, there's a whole list of things people would say in the 60s, when we can do this, we'll know we have AI. When we can do an integral, like from a calculus course, when we can do this and that, we'll know we have AI. When we can sort of do a conversation with a computer and have it seem like a human. Well, at this point, one of the things that had seemed to be difficult there was, well, gosh, the computer just doesn't know enough about the world. You start asking the computer, what day of the week is it? I might be able to answer that. Who's president? Probably can't answer that. These kinds of things. And at that point, you kind of know you're talking to a computer, not to a person. At this point, when it comes to these sort of Turing tests, conversational tests of AI, people who've tried connecting, for example, Wolfram Alpha to their Turing test bots, they lose every time. Because all you have to do is start asking it sophisticated questions, and it can answer them, and no human can do that. By the time you've asked it a few different, disparate kinds of questions, there'll be no human that knows all of those things. but yet the system can know them. So in that sense, we've achieved really good AI at that level. Now there's another branch, which is there are certain kinds of tasks that are sort of very easy for humans that have traditionally been very hard for machines. Standard one is visual object identification. What is this thing? Right? We can know what this is. We have some easy description of it, but the computer is just hopeless at that. Well, in the last basically year, that completely changed. So, for example, in March, April, sometime early this spring, we brought out a little image identification system, website, etc. And a bunch of companies have done somewhat similar things. I think ours, for various somewhat interesting reasons, is a little better than other people's. It doesn't deserve to be better, but it happens to be somewhat better. And what it does is you show it something, and for about 10,000 kinds of things, it will tell you what it is, and it does a pretty good job. You can. It's fun to try and confuse it. It's fun to show it an abstract painting and see what it thinks it is, but it basically does a pretty good job of saying what it is. How does it work? It works using the exact same technology, basically, that McCulloch and Pitts kind of imagined in 1943, that lots of us worked on in the early 80s for neural networks. And so the question is, what happened that made it work now and didn't let it work then? Well, if you look at what the system actually does today, there are maybe 5,000 picturable nouns in English, common nouns which you can make pictures of. Maybe 10,000 if you include somewhat specialized things like special kinds of plants and beetles and things that people can, with some frequency, recognize. Well, the thing that we can now do is we train it on 30 million images of all these kinds of things, and it's this big, complicated, messy neural network. Probably doesn't matter much what the details of that neural network are. We do this training. It takes about a quadrillion GPU operations to do the training. And at the end of it, it does a pretty good job of recognizing 10,000 kinds of things. And we, as humans, are impressed by this because it's pretty much what we humans can do. And it pretty much had about the same training data that we have. It's about the same number of images that a human would see in the first couple of years of their life. It's about the same number of operations that have to be done to do the training. It's about the same number of neurons in the kind of at least the first levels of our visual cortex. The details are all different. The actual way that these artificial neurons work is little to do with the way that actual neurons in the brain work, but it's conceptually similar, and there's a certain kind of universality to what's going on, that you have this essentially really what it is at a sort of more mathematical level. It's this thing that's a composition of a very large number of functions that has certain continuity properties that allow you to effectively use calculus methods to incrementally train the thing. And once you have those attributes, you, it seems, can end up with something that does the same kind of job that we do in doing visual object recognition. And it's actually interesting because back in the 80s, people had very successfully done OCR, optical character recognition. So they were able to take the 26 letters of the English alphabet and so on and say, okay, is that an A, is that a B, is that a C, and so on. That could be done for 26 different possibilities, but it couldn't be done for 10,000 possibilities. And it's really just a matter of the scale of the whole system that makes that possible today. But as a kind of a have we got to AI yet? These are important components. I mean, there are basically a few of these. There's visual object recognition, there's voice to text, and there's language translation. And those are kind of three kinds of things which humans manage to do with varying degrees of difficulty. I can't do language translation for any human language, really, maybe Latin a little bit. But people can learn to do human language translation. These other two, voice to text, well, people learn to do that. And visual object recognition, people are they learn in the first couple of years of life, like it or not, to do that. So the thing that these become essentially, these are some of the missing links to how do we make machines that are kind of human-like in what they do. And for me, one of the interesting things has been sort of incorporating those capabilities into a precise kind of symbolic language. And there's a whole lot of stuff to say about that is a kind of a 500-year story about what we now need to do in terms of having a symbolic language to represent the everyday world. I mean, we now have the capability to say, you know, this is a glass of water or something. Now we actually have to find a good, we can go from picture of glass of water to the concept of a glass of water. Now we have to have some actual symbolic language to represent those things. And, you know, in my own efforts, I, you know, started off trying to represent kind of mathematical, technical kinds of knowledge, and then went on to lots of other kinds of knowledge. I think we've got a pretty good job done now of sort of systematic objective knowledge in the world. Now the question is to represent kind of everyday discourse and the kinds of things that people say to each other in a precise symbolic way. And there are certain kinds of, you know, you might have in a precise symbolic representation, you might say X is greater than 5. Okay, that's a sort of predicate. You might also say, you know, I want a piece of chocolate. That's also a predicate. But it has an I want in it, rather than a, you know, sort of chocolate has higher calorie value than such and such. And so we have to try to find a sort of symbolic representation, a precise representation of these kinds of things that we have traditionally expressed in human natural language. And actually, I've been interested in this. This is one of the things I'm thinking about these days, and it's kind of interesting because I like to do my homework, and I like to find out what have other people figured out about this. And so I start reading literature about this, and most of the literature points back to the 1600s. And there was a lot of people like Leibniz in the late 1600s, a man called John Wilkins. These were the people who there was this period when there were these things that they called philosophical languages. And the idea of a philosophical language it was essentially what I'm now trying to do, a symbolic representation of the world. The one thing that I really like is I look at the philosophical language of John Wilkins, and you can see how did he divide things that were important in the world. And it's somewhat sobering, but somewhat pleasing in some ways. Some aspects of the human condition have been the same since the 1600s. There's the same types of issues that come up, and some are very different. I mean, the whole section on death and various forms of human suffering is huge at that time, and in sort of today's ontology would look a lot smaller. Big achievement. There are also other aspects of it's interesting to see, how would a philosophical language of today differ from a philosophical language from the mid 1600s, and this is a measure of progress, I think, to see how that what kind of difference there is there. So this is one of the things that I like to be able to do, is to have a sort of symbolic representation of everyday discourse in the way that we now have a symbolic representation of sort of systematic discourse. I mean, there are many of these sort of attempts at formalization that have happened over the years. I think in mathematics, for example, Whitehead and Russell, 1910, their Principia Mathematica, that was the sort of the great effort to the biggest show-off effort, at least. There had been previous efforts by Frege and then Peano that were a little more modest in their presentation, to try and see how would you formalize, in that case, mathematics, in a sort of precise system. It's sort of interesting what they managed to do right, what they did wrong. Ultimately, they were wrong in the idea of what they thought they should formalize. They thought they should formalize some kind of process of mathematical proof, which turns out not to be the thing that most people care about. But you had asked about what will be a modern Turing test, what will be a modern analog of Turing tests. It's an interesting question. I mean, I think that there's sort of the being able to have the conversational bot, which is kind of Turing's idea, that's definitely still out there. That one hasn't been solved yet. It will be solved. The only question is, what's the application for which it is solved? And for a long time, I had been, kind of like a why do we care type thing, because I was thinking the number one application was going to be customer service. And while that's a great application, it's, in terms of my favorite way to spend my life, that isn't particularly high up on the list. What I realized, though, about the Turing test and things like customer service, because customer service is precisely one of these places where you're trying to interface between, you're trying to have a sort of conversational thing happen. One thing I realized is that the one big difference between Turing's time and our time is that our method of communicating with computers, there's one huge difference, which is in his time, what he imagined was it's a conversation. You say some things to it, or you type some things to it, type some stuff back. in today's world, it shows you a screen back. And actually, the case that I was curious to see a few years ago was, you go to a movie theater. There's, you can buy a movie ticket from a person. You can buy a movie ticket from a machine. So there was the question of at what point, people like me who always like to use the latest, techno toys, as soon as those things appeared in movie theaters, right, I was using the machine only, right? And for a long time, there was nobody else using the machine. And then in urban movie theaters, you started to see more and more people using the machines. And now most people, I think, use the machines. But one thing that's interesting about those machines is how is the transaction with the machine different from the transaction with a human? And the main answer is there's a visual display on the machine. And so, you say, it might ask you something, but you just press a button and you can see immediately, you can use your eyes to understand something, your visual system to interpret something, which is a little different. And so, for example, in Wolfram Alpha, you ask it something, and when it's used inside Siri, if there is a short answer, will say back the answer, the short answer to you. But what most people want is the visual display of the big report that shows, the infographic of this or that. So this is something which is sort of interesting because it's a non-human form of communication that turns out to be richer than traditional human communication. I mean, that is, if we were all incredibly fast, perfect artists, we could, as we're talking, we could draw that infographic and say, this is what I'm talking about. But in fact, in most human-to-human communication, we're left with pure language, whereas in computer-to-human communication, we have this much higher bandwidth channel of visual communication that turns out to be important. And so the traditional Turing test, I think, is a little bit, it's a little funny because many of the most powerful applications kind of fall away because we have this additional communication channel. So, I've been interested. So, for example, here's one that we're actually trying to pursue right now, is a bot to communicate about writing programs. So you say, I want to write this program, I want it to do this. It says, it'll say, well, I've written this little piece of program, here's what it does, is this what you want, blah, blah, blah. It's a kind of a back and forth bot. There's also other kinds of bots that we've looked at, things like tutoring bots, where it's like, okay, you should understand this piece of chemistry or something. And how do you, and that's interesting because it's actually kind of an interesting problem because you have to make a model of the human. That is, if you're trying to explain, what is the right thing to say at this point? Do you explain, this? Okay, what is the human confused about? You have to have a model of the human to know what they're confused about, and so on. And I think it's but what has been difficult for me to understand is, in the case of, when do you achieve a sort of Turing test AI type thing? It's like there isn't the right motivation. There's not the right. One could, as a toy, one could make a little chat bot that people can chat with, but I don't think, and I think that will be the next kind of. We can see the current round of deep learning, particularly recurrent neural networks and so on, can make pretty good models of human speech, and so and human writing and so on. So it's pretty easy to type in, you say, how are you feeling today? And it kind of knows that most of the time when somebody asks somebody, how are you feeling today, this is the type of response you give. And for example, one of the toys, actually, I've been playing with this a little bit. I want to figure out whether I can automate responding to my email. I know the answer is no. The sign when, a good Turing test for me will be, when can I have a bot respond to most of my email? It's this is and that's sort of an interesting. I mean, it's a tough test because some aspects of the email, like I don't care about this, throw it in the spam folder type thing, that's comparatively easy. But if it's somebody says, what should we do about this inconsistency in some design of our product of this and that and the other, to be able to answer that in any way that's, to be able to say, do you approve this thing? To be able to answer that with any reasonable degree of confidence is hard. I mean, the thing to realize about that is most of those answers, one has to learn them from the human that the email is connected to, so to speak. I mean, I think I might be a little bit ahead of the game because I've been collecting data on myself for it's now about 25 years. So I have every piece of email, every keystroke I've typed for, well, every piece of email for 25 years, every keystroke for maybe 20 years or something, and lots of other stuff like that. So in a sense, I should be able to train an avatar, an AI, that, will do what I can do, perhaps better than me, more easily than most. One of the things I think is kind of interesting to think about is in a world where AIs are figuring out a lot of stuff for us, people worry about the scenario, oh my gosh, the AIs are going to take over. My belief about that scenario is that something much more, in a sense, amusing will happen, at least first, which is that it will quickly become the case that the AI can figure out, it knows what you intend to do, what you want to do, and it's really good at figuring out how to get there. And so, just like, with a car GPS, we tell it we want to go to this destination, and people like me just, I don't know where the heck I am, I just follow my GPS. Years ago, when GPSs were much younger, that led to things my children are always amused by the fact that I had a very early GPS, and it was like drive this way, this way, this way, and we actually were on one of these piers going out into Boston Harbor, and that was it's like I just follow the GPS. But what will happen more to the point is that there'll be an AI that knows our history and knows, oh yeah, you're probably going to, on this menu, you're probably going to want to order this, or on this, you're talking to this person, you should talk to them about this. I've looked at your interests, I know something about their interests, these are the common interests that you have, these are some great topics that you can talk to them about. And more, people, the AIs will suggest what we should do. And I suspect people will, most of the time, just follow what the AIs tell them to do, because they'll probably be better than what they figured out for themselves. And so I think, to me, this is the AI takeover scenario that happens is the laziness of the humans. It's not really laziness. It's like, take good advice. The AI is telling you what to do. It's better than what you would have figured out for yourself. Just do what the AI says. It's there's sort of a complicated interaction of, in terms of technology and so on. It's there's this question about you can do terrible things with technology, you can do good things with technology. People will always be people, and some people will try and do terrible things with technology, and some people will try and do good things with technology. I think one of the things that I really like about technology today is the kind of equalization that it's produced across lots of kinds of people. I mean, there was a time when I used to be very proud that I had the best computer of anybody I knew. But now I have the same computer as pretty much anybody I know. And we have the same smartphones, and pretty much the same technology can be used by a decent fraction of the 7 billion people that exist. It's not perfectly flat, but it's reasonably flat. And I think we'll see the same type of thing in lots of other areas of technology, whether it's medical technology, other kinds of things, where, in a sense, I don't know whether it's luck or whether it has to be that way, that these pieces of technology that one's producing are very broadly, can be very broadly available. It's not the case that there's a sort of the king's technology is different from everybody else's technology. And I think that's that's an important thing. Now, in terms of how, one of the things that I always notice, because we make stuff that we sell to people and people use all over the world, and I've sometimes we've even thought about publishing these indices of how much does Mathematica get used, how much does Wolfram Alpha get used in different countries around the world, because a huge amount from that. Which cities, and all kinds of stuff. And, there are countries which are really very technologically sophisticated. There are countries where they're really not. I think we can. And so it's sort of an interesting thing to me today. The great frontier, I think, 500 years ago it was literacy. Today it's doing programming of some kind. Today's programming will be obsolete in not very long. In other words, for example, when I was first using computers in the 70s, people would say, well, if you're really a serious programmer, you've got to be using assembly language. Now, I often ask these computer science graduates, did you learn assembly language? They say, well, yes, I had, it was a section 1 class about assembly language. Okay, why do people not learn assembly language? Because basically computers are better at writing assembly language than humans are, and it's only a very small set of people who need to know the details of how, language gets compiled into assembly language and so on. Well, a lot of what's being done by armies of programmers today is similarly mundane. It's stuff where the goals can be described much more succinctly, and it turns into some giant blob of Java code or JavaScript code or something, and there's actually no good reason for humans to be writing all that stuff. And that's what people like me try to do, is to automate that so that we can automate the process of programming. So what's really important is just going from what the human wants to do to getting the machine as automatically as possible to get that done. Now, the thing that's interesting right now, one of the things I'm really interested in right at this moment, is this sort of the equalization that this is producing. Because it means that in the past, if you wanted to write a serious piece of code, a program that did something important and real, it was a lot of work. You had to really know quite a bit about software engineering. You had to invest months of time in it. You had to, if you were you'd have to hire programmers who knew this. You'd have to learn it yourself. Whatever, big investment. Now, the big achievement from having automated a lot of the stack is that's not true anymore. A one-line piece of code, even a thing you can tweet sometimes, already does something interesting and useful. And that means that it sort of unlocks a vast range of people who couldn't previously make computers do things for them, to let them make computers do things for them. And so now what happens? Well, so one of the things I'm interested in is at this point, kids and fancy professionals are really at the same level in terms of what they can do in terms of teaching computers, telling computers what to do for them. And so now one of the things I'm interested in is how do you teach that kind of computational thinking and programming to as broad a range of people in the world as possible. And one of my sort of little private things I really would like to see is for there to be a large number of random kids around the world in random countries who learn sort of the new kind of capabilities of sort of knowledge-based programming and so on, and get to the point where they can produce code effectively that's as sophisticated and as anybody in the fanciest kind of most educated places can. And I think I think this is within reach. I think we've got to a point where sort of anybody can learn to do sort of knowledge-based programming, and more importantly, can learn to think computationally, because the actual mechanics of the programming are pretty easy now. What's difficult is imagining things in a computational way and thinking through how do we conceptualize this activity that we have in some computational way. And so one of the things I'm sort of interested in is how do you teach computational thinking? And this is, we've had, in mathematics, for example, there's 1,000 years of history about how we teach mathematical thinking. And we know to the level of, which chapter of the book goes here and there. And it's like, I was just asking yesterday, actually, we were talking about, for some initiative we have, I was asking about calculus books. And I think they always have 14 chapters, if I'm not mistaken. And I asked, how long have they had those same 14 chapters? And the claim was that the very first calculus book, written by Colin Maclaurin in 1727, had some of the same structure. Many of the examples were the same. So it's been something which has been developed over a long period of time and is very precisely known, sort of how you feed mathematics to the humans. So a couple of points to make. First of all, in the case of, if you're writing Wolfram language code, then I'm ultimately responsible for the design and structure of how the language works. In the case of, DNA code and biology, there's nobody you can point to and say, you're responsible for, you designed this. It's something that has evolved over a long period of time. And much like human natural language, it is going to have there's some degree of complexity in knowing what it's going to do. When you it should do what the designer thought it should do. Now, which is not to say that it isn't super useful to program living systems, not least because we are living systems, and because living systems are the only example we know of successful molecular computing. I mean, we may, there may come a time when we've managed to engineer things, when we've managed to design a lifelike thing that is sort of as designed as a computer language is today. But we're not at that point. So we have to be using the molecular computer that we have, which is us and our biology. Now, in terms of how to do that programming, I think it's a super interesting question. I think that there's been kind of if you look at the nanotechnology tradition, there's been this kind of idea that how do we achieve nanotechnology? Answer, we take technology as we understand it at a large scale today, and we make it very, very small. So we say, how can we make a CPU chip that is, on an atomic scale? Well, maybe we'll make it mechanically, but fundamentally we're using the same architecture as a CPU chip that we kind of know and love. I think that isn't the only approach one can take, and a lot of the things I've done looking at simple programs and what they do suggests that you can have even very, very simple, very kind of impoverished components, and with the right compiler effectively, you can make them do very interesting things. And I think that is my own guess is there's one of these projects of sort of doing molecular scale computing that I've wanted to do for so long, and I just don't quite think that the ambient technology is to the point where one wouldn't have to spend a decade, building ambient technology to get to the point. I'm kind of hoping that we're almost at the day when it's possible for somebody like me who isn't going to build all that ambient technology to actually do something with molecular computing. But I think my guess about how one would do that, how one could do that, is to say, okay, we've got these components. These components are enough to make a universal computer, and you might say, well, I don't know how to program with these components, but by doing sort of searches in space of possible programs and so on, one starts to build up building blocks that one can then create a compiler for it. And the surprising thing is that surprisingly impoverished stuff is capable of doing sophisticated things, and the compilation step is not as gruesome as one might expect. In other words, one might think, oh gosh, if it's only, a little, I don't know, like I have this very tiny Turing machine, that's the simplest universal Turing machine that has 2 states and 3 colors, and has a little tiny rule that you could write it in English. It'd probably be a long sentence long, but you could make a picture of it. It's really tiny and simple. That Turing machine, you might ask the question, how can I actually compile a program that I might care about down to that Turing machine? I haven't done it, but I think that what one will find is that there's a layer of nasty, messy sort of machine code, and then above that, it gets pretty simple. And that layer of nasty, messy machine code will add some inefficiency, maybe a factor of 10,000, maybe more, but a factor of 10,000 is nothing when you're dealing with the scale of molecules as compared to sort of large-scale things. And so, I guess my own prejudice and thought would be that sort of the searching the computational universe and trying to sort of find programs that are interesting, find building blocks that are interesting, is a good approach. I think that a more traditional engineering approach that says, let's try to, by pure thought, figure out how we build stuff, my guess is that's a harder road to hoe. I mean, it doesn't mean it can't be done, but my guess is that one will be able to do some really amazing things by just saying, these are the components, we have a good representation for them, what can we now, let's search the possible programs we can make with these things, now what can we, now the question is, one might say, well, we can get this combination of molecules, will do all kinds of fun things, it will make this big blob of stuff, it will do this, it will do that. We might say, but what do we care? And then we have to answer the question, it's back to this question about connecting kind of human purposes to what is available from the system. I mean, one question is, what does the world look like when many people know how to code? Coding is a form of expression, just like English writing is a form of expression. To me, some simple pieces of code are quite poetic. They express ideas in a very clean way. That's very, you look at it and you say, that's, there's kind of an aesthetic thing, much as there is to expression in a natural language. But now, in general, what we're seeing is there's sort of this way of expressing yourself. You can express yourself in natural language, you can express yourself by drawing a picture, you can express yourself in code. One feature of code is that it's immediately executable. It's not like when you write something, somebody has to read it, and the brain that's reading it has to separately absorb the thoughts that came from the person who was writing it. I mean, the thing I've realized, again, one of the things I'm thinking about right now, that I'm very frustrated I can't figure out. I'm sort of on the cusp, but I haven't got there yet. So what I realized is that if you look at sort of how knowledge is transmitted in the history of the world, so to speak, one form of knowledge transmission is essentially genetic. That is, you have an organism and its progeny has the same features that it had. Okay, so that's sort of level 0. Level 1 is the kind of knowledge transmission that happens with things like visual object recognition, where the new critter is born, it has some neural network, the neural network doesn't have anything, it has sort of random connections in it, but as the critter goes around the world and it starts recognizing different kinds of objects and it learns that knowledge. So it's kind of something which without any, and that's what throughout the animal kingdom, critters have been learning visual object recognition. Okay, so that's sort of the next level of knowledge. Then there's the level of knowledge that was sort of big achievement of our species, which is natural language. The ability to take knowledge and represent it abstractly enough that we can communicate it sort of in a disembodied way, brain to brain, so to speak, that we don't have to, the individual brain doesn't have to relearn from the raw material. The knowledge can be taken abstractly and communicated to the next brain down the line, so to speak. And, arguably, the natural language is kind of, arguably the most important invention in sort of our species and in human history. And it's what led to, in many respects, our civilization and many, many other things. So it's like really important. Well, now we've actually got another level of this, which is with, and probably one day it will have a more interesting name, but with essentially knowledge-based programming and so on, we have a way of taking a representation of knowledge in the world. It's an actual representation of the world. It's not just a mathematics or computer language or something. It's a thing that represents, real things in the world, but it does so in a precise symbolic way that has this feature that not only is it understandable by brains and communicatable to other brains and to computers, it's also immediately executable. And I'm pretty sure that this is really a big deal. I mean, I'm pretty sure that just as in some respects natural language gave us civilization, there's the question of what will knowledge-based programming give us. And one bad answer is it'll give us the civilization of the AIs. That would be kind of disappointing for the humans. That's kind of what we don't want to have happen, because there could be a point at which the AIs are doing a great job. They're communicating with each other, they're doing all these kinds of things, and we're pretty much left out of it because there's no intermediate language, there's nothing that sort of interfaces with our brains. Anyway, so one of the questions that I'm super interested in right now is this question of, in this sort of fourth level of knowledge communication, what is the big thing that would lead to? And I kind of think, if you were, caveman Og or something, and you were just realizing that language was starting, it's like, could you imagine civilization from that point? And it's, you'd have to, and I feel like, what should we be imagining right now? And this relates to this question, even for humans, if most people could code, what would the world look like? And there are clearly many trivial things that would change, contracts are written in code, restaurant menus might be written in code, and you could say, this is how the food's going to be made. Okay, I want to change this piece and that piece, and so on. Things like this. There are things, there's sort of simple things like that change. But I think probably there are much more profound things that change. I mean, the rise of literacy gave us some things that, gave us bureaucracy, for example, which didn't really, it had existed in the past, but I think it dramatically accelerated the bureaucracy, for better or worse, gave us, I think, sort of greater depth of governmental systems and so on, for better or worse. But I think and so there's a question of what does that look like in the case where most people can code. Now, when you ask about how does the sort of the coding world relate to the culture world? Well, so one of the things I've been thinking about recently is when we think about, for example, high school education, and there's a question of, okay, how do you teach programming, coding, that kind of thing, computational thinking at high school level? And one of the possibilities is, well, you have a course about that and you tack it on to all the many, many, many things that people are being taught today. The other possibility that's much more interesting is you just rethink all the existing areas and you say, well, if we also have computational thinking, how does that affect how we study history? How does that affect how we study languages, social studies, whatever else? And the answer is, it has great effect. I mean, there's a lot of things that you can, for example, imagine you're writing your essay. Today, the raw material for a typical kid's essay is, well, I read something and this is the raw material, now I'm going to write what I think about that. It is not the case that kids can generate new knowledge very easily. But sort of in the computational world, that's no longer true. It's very straightforward for a kid to go and, if they know something about writing code, to go to the, beautifully digitized historical data and so on, and go figure out something new. And then you're writing an essay about something where you say, this is what I discovered today, so to speak, and now I can write an essay about it. So I think that's part of the way that, I don't think it's sterile at all. I think this is the achievement of knowledge-based programming, is that it's no longer sterile. And the reason is because it's got the knowledge of the world sort of knitted into the language that you're using to write code. So if you take mathematics as an example, right? So there's right now, there's this area that people teach, which is sort of the pure mathematical area. But at least basic math gets into all kinds of places. It hasn't gotten so much into the humanities, but it's something where it's just part of the way we think about things is sort of at least basic math. So similarly, computation is something that in these times is part of the basic way we should think about things. And the great thing about computation is that if we think about things in terms of computation, then the things become sort of immediately executable. They become things where once we have the idea computationally and we know a little bit of the mechanics of how we write code, it's pretty straightforward mechanics, then given that idea, once we've formulated it computationally, we can then get the machines to go do the work. And a kid can get machines to do the work just the same way as the fancy researcher can do it. Right. I mean, what I was saying earlier was I think this is the big issue. An AI on its own does not have a goal. Goals are a human construct. So the thing that came out of lots of science stuff I've done is this realization that sort of intelligence and computation are kind of the same thing. And there's computation all over the universe, whether it's in a turbulent fluid producing some complicated pattern of flow, whether it's in some, celestial mechanics thing of some interaction of asteroids with this, that, and the other, whether it's in brains and so on. And so this question of, does it have a purpose, right? What is its goal? You can ask that about any of these systems. Does the weather have a goal? Does climate have a goal? And this is unfortunately, this is one of these things which people have been asking this since Aristotle, right? And this is this is kind of the final cause question and so on for Aristotle. And one can unpack it a little bit. So this whole sort of, does the thing have a purpose? So let me try and unpack it a little bit. I don't claim to have completely unpacked this question, but one question is, can you tell if a thing has a purpose? Okay, was this made for a purpose? So look at Stonehenge, for example. Was Stonehenge made for a purpose? Was presented with a thing, was it made for a purpose? Now, a lot of stuff that we see today, it's very obvious that it was made for a purpose by humans because it has a lot of the vernacular of human engineering history. So, we see a thing with cogs and, the Antikythera device, when people started looking at this lump of gunk that was, dredged up from the, 100 BC to 100 AD period, shipwreck, was it made for a purpose? Well, when it was dropped and broken in two, there were little cogs sticking out. And we kind of immediately know this is made for a purpose, and it isn't just a pile of gunk, because that's part of the history of human engineering. And so, given the history, it's very easy to recognize human purpose in things. I mean, this is it's a little bit similar to this question of, is it alive or not? On Earth, it's very easy to answer the question, is it alive or not? We look at fairly easy. We look at, does it have RNA? Does it have cell membranes? Does it have these kinds of things that come from the history of life on Earth? I remember when I was a kid, the first Mars landers were landing, right? And I remember this: is there life on Mars, right? And is the green stuff that seems to happen every season, vegetation or whatever? And I remember I was really curious, what would the tests be? And from today's time, they're pretty amusing. I mean, the basic test that was used was scoop up a piece of Martian soil, feed it sugar, and see if it eats it. That was the top test of is it alive. Now, I don't think any of us would believe that life has to be something that eats sugar. But the question of what is the abstract definition of life, that's really hard. And it's tends to be very sort of, anyway, but back to this question of purpose. How do you recognize purpose? So there are a bunch of other cute examples you can give. So one example is, look at the Earth from space. Can one tell that there's anything with a purpose hanging out on the Earth? Can one tell that there's civilization on the Earth? And it's so I did this experiment maybe 15 years ago now. I asked astronauts, what do you see on the Earth that shows you that there's intelligence on the planet, so to speak? And the first thing I was told was, in the Great Salt Lake in Utah, there is a straight line. That turns out to be a causeway that divides what turns out to be two areas that have very different colors of algae. So it's a very dramatic straight line. It's like, okay, there's a straight line. And I found, then I was interested, where's the longest straight line made from lights? There's a road in Australia that's really long and straight, and there's a railroad in Russia, I guess in Siberia basically, that's really long and that has sort of a lights that go on, when it stops at stations and things, there are lights there. So you see some straight lines and things. And then another good example is in New Zealand, there's a more or less perfect circle. It's called Mount Erebus. Okay? So I was doing this research, I guess maybe more than 15 years ago now, before the web was common. Right? So you couldn't just go look up all sorts of attributes of this. So anyway, we got in touch with, we were trying to get maps of the thing and so on, and we were in touch with the New Zealand Geological Survey, what they're called. And they said, if you're writing a textbook, please do not say that Mount Erebus is a circular volcano. The circle does not come from the volcano. The circle comes from a national park that was drawn around the volcano, and there are sheep or something that graze, inside the national park but not outside, or the other way around. And that's what leads to the circle. So this is another example of human, there's a piece of geometry that comes from the humans. But it's pretty difficult to find really clear examples of sort of obvious purpose on the Earth as viewed from space. And I think, the other question that comes up, it's a great sort of question for the extraterrestrials, so to speak. Okay, if we want to recognize extraterrestrials out there, how do we tell if the signal we're getting has a purpose? So, 1968, pulsars discovered, every few milliseconds, I guess, how long was the first pulsar? I forget, but something between milliseconds and seconds. You hear kind of this flutter-like sound that's a periodic thing, and at the time it was the first question is this a beacon? Because what would make a periodic thing like that? It must be for a purpose. Well, actually, it turns out it's just a neutron star rotating. But this question comes up over and over again: what gives evidence of a purpose? And in fact, back in the early 1900s, I guess. Marconi and Tesla were both people who were sort of listening to radio transmissions from away from the Earth, and there was sort of a question. I think Marconi had a yacht, and I think in the middle of the Atlantic, you could hear these kind of weird sounds that sound a little bit like whale songs, but they're kind of they come from radio type things. And the question, I think Tesla was very much on this is the Martians signaling us type thing. How does one tell? In fact, it's some modes of the ionosphere that are effectively a magnetohydrodynamic phenomenon. They're just physics, and this is one of these cases of like the weather has a mind of its own, so to speak. How do you tell whether it's a thing which has a intelligence and a purpose and all that kind of thing, or whether it's just magnetohydrodynamics of the ionosphere? And how do you tell if a thing has a purpose? It's hard. One criterion that I think one can potentially apply is, does the thing achieve, if you can identify a purpose, is it minimal in achieving that purpose? That is, if you see a thing and it's mostly, a fork that you eat with, but it has incredibly elaborate ornamentation on it. You say, well, its purpose is it's a fork, but it also has all this ornament, which is not relevant to its purpose. Now, the ornament may itself have a purpose to give people a different emotional reaction to their fork or whatever else it is. But what is this question of, is something minimal for its purpose? And does that mean that it was built for the purpose? So when you look at a thing, there are typically different explanations you can give for what happens. One is the mechanistic explanation. It does this because the ball rolls down the hill because at the next moment of time the gravitational pull will do this and this and this. Or the ball rolls down the hill because it's satisfying, the principle of least action, and it is globally trying to optimize this particular thing. And you can, there are typically these two explanations you can give for something: the mechanistic explanation and the, teleological explanation. And the question of which is the winning explanation, which is the right explanation, if they're even, is, so one possible criterion is the thing was built for a purpose if it is minimal in achieving that purpose. The problem is that essentially all of our existing technology fails that test. We can imagine technology that works that way, but most of what we build is absolutely steeped in technological history and is incredibly non-minimal for achieving that purpose. I mean, if you look at a CPU chip, there's no way that's the minimal way to achieve what the CPU chip achieves. Yet, it's steeped in all this history of our engineering technology. So anyway, this question of how do you identify if a thing has a purpose, I think is really hard. I think it's really, for example, for the extraterrestrial question, it's really important because it's like, one good thought experiment is, imagine that the extraterrestrials could arrange stars however they want. How would they arrange them to show that they were arranged for a purpose? Would they put them in a straight line? Probably not, because we can imagine all kinds of physical processes which might do that. But they sure wouldn't put them in equilateral triangles, because there's a particularly simple physical process that does that. Would they have a buy Coke sign? Would they have some piece of alien artwork? We would undoubtedly not recognize the alien artwork as having a intelligent purpose and so on. So I think it's an important question, because when we look at radio noise from the galaxy, it's very similar to the CDMA transmissions from cell phones. It's not fundamentally different from that, and those transmissions use pseudo noise sequences which happen to have certain repeatability properties, but they come across as noise, and they are actually set up as noise for the purpose of not interfering with other channels and so on. So it's really a funny thing. How do we recognize sort of a fundamental purpose? And the whole thing gets even more messy when we ask a question like, if we observe primes being generated from, a sequence of primes being generated from a pulsar, we say, what generated these? Did you need a whole civilization that would grow up and discover primes and make computers and do this and make radio transmitters? Or is there another explanation that's just that some physical process makes primes? And then that physical process may have all kinds of weird things going on inside it. I mean, there's a little cellular automaton I made up once that makes primes. And you can see how it works. If you take it apart, it just has little things bouncing around inside it, and out come a sequence of primes. And but that didn't need the whole history of civilization and biology and so on to get to that point. So it's really a slippery thing, whether, when you observe something, was it created for a purpose? How do you tell if it has a purpose? These kinds of things. I don't think there is an abstract sense of purpose. I don't think there's an abstract meaning to, in other words, I think what you end up with is the universe, you're ending up with this weird thing where you have to say, does the universe have a purpose? Then you're doing theology in some way. Does it, there isn't abstract purpose, I think. I think there's no meaningful sense in which there is an abstract notion of purpose. That is, that purpose is something that comes from history, and it comes from, one of the things that might be true about computation, might be true about our world, that would be kind of disappointing, is maybe we go through all this history of biology and civilization and so on, and at the end of the day, the answer is 42 or something. And that's just, that's the end, so to speak. That's that we got to the answer. And we say, you went through all of that, what a crazy place. You went through all these 4 billion years of, various kinds of evolution and so on, and all this stuff, and then you got to 42. Well, actually, nothing like that will happen, because there's this notion of computational irreducibility, which is kind of the thing that comes from Gödel's theorem of universal computation and so on, that there are computational processes that you can go through, and that things often go through, where there's no way to shortcut that process. In other words, you can't just know, you can't say, oh, you were wasting your time. I mean, much of science has been about shortcutting computation done by nature. So, for example, if we want to, we're doing celestial mechanics, we say, let's predict where the planets will be a million years from now. Well, we could just follow the equations, follow each step, and see what happens step by step. But the big achievement of, when we think there's a prediction in science, it's because we're able to shortcut that and just jump from where we are now and reduce the computation. We're able to be smarter than the universe and figure out, this is the end point without going through all the steps. And that's been the sort of story of prediction in science. But the good news is, in a sense, it's bad news for science. It's good news for us having meaningful lives, so to speak, that there isn't a way to just say, okay, we can shortcut everything. We can, with a smart enough machine, with smart enough mathematics, we can always just jump ahead and get to the end point without going through all the steps. We actually have to irreducibly follow through those steps. And that's, in a sense, that's why history means something. If it was the case that we could get to the end point without going through the steps, we would, in a sense, history would be, in some sense, pointless. We wouldn't, So I think this fact that, bad for science because we can't make these predictions, but good for the meaningfulness of sort of the history of civilization and so on, is that, these details are irreducible. And I think, in a sense, when one realizes that sort of everything can have these attributes like intelligence and so on, one realizes that if we are going to distinguish that the thing that has to be special about us is all of these details about us. It's not going to be some big feature. Like, it's not going to be the case, as I thought it once that it was, that there's us that's intelligent and there's everything else in the world that's not. It's not going to be some big abstract difference between us and the clouds and the cellular automata and the whatever else. It's not an abstract difference. It's not something where we can say, look, this brain-like neural network is just, qualitatively different than this cellular automaton thing. Rather, it's a detailed difference that, this brain-like thing was produced by this long history of civilization, et cetera, et cetera, et cetera, whereas this cellular automaton was just created by my computer in the last microsecond. I think it's but my belief about, the problem of the abstract AI is very similar to the problem of extraterrestrial intelligence. It's the recognition of when does a thing have a purpose, when is a thing intelligent. These are again, these are questions I don't consider that I've answered. I'd be very, of course, one of the great things in science is why have we not found any extraterrestrials? Why, how could we possibly be this unique? And, to what extent, but maybe that's a silly question, because maybe there's intelligence all over the universe. And we have to then ask, well, just how close is it? Does it have RNA? Does it have, did it invent a notion of democracy or something? And, a lot of these other attributes, like that we think of, a lot of when we start trying to break down and say, well, it will be intelligent, our AI will be intelligent if it can do blah, 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 if it can find primes, if it can produce this and that and the other. there are many other ways to get to those results, and that's a consequence of the fact that there just isn't a bright line between intelligence and mere computation. I think that's in a sense, it's a disappointing, it's another part of the Copernican story, so to speak. We used to think, Earth's the center of the universe, all this kind of thing, and now at least we think, gosh, we're special because we have intelligence and nothing else does. And I'm afraid, the bad news in a sense is that really isn't a distinction. And by the way, that lack of a distinction, I think, is pretty critical for thinking about the future of the human condition. Because here's one of my sort of, a scenario that I'm really curious about. Let's say there's a time when human consciousness is readily uploadable into digital form, everything can be virtualized and so on. And pretty soon we have, a box of 1 trillion souls. There are 1 trillion souls, they're in a box, they're, all virtualized. And we look at this box, and in the box there'll be, hopefully nice molecular computing, maybe it'll be derived from biology in some sense, but maybe not. But there'll be all kinds of molecules doing things, electrons doing things, the box is doing all kinds of elaborate stuff. And then we look at the rock that's sitting next to the box. And inside the rock, there's all kinds of elaborate stuff going on, all kinds of electrons doing all kinds of things. And we say, what's the difference between the rock and the box of 1 trillion souls? And that's where, and the answer will be, well, the box of 1 trillion souls has this long history, and the details of what's happening there were derived from the history of civilization and and people watching videos made in 2015 or whatever, and all these kinds of things. Whereas the rock, well, it came from this geological history, but it's not a history that is like it's not the particular history of our civilization. But I think this is this question of realizing that there isn't sort of this distinction between intelligence and mere computation leads you to these things like, imagine the future of civilization ends up being the box of 1 trillion souls, and then what is the purpose of that? What do we, for example, from our current point of view, in that scenario, it's like every soul is playing video games basically forever, and the question is, what do they, what's the kind of the end point of that?